Hello friends, I welcome you to this video. This video is specifically for those doing Physics A-Level Paper 4. Of course, this video is specifically dedicated to my students. This is a correction of their end of term. This is year 12, specifically in our school it's called year 12, but in other schools it's grade 12. But of course, this is a paper that they have done, and I hope that when I go through this paper, it might be of use, of help to another student elsewhere. So to my year 12 students, this is your correction. So all you need is to pull out your question paper that you did, and then you follow through the corrections as they are being done in this video. So I am starting with one of the papers which you did. Actually, this was, I called it paper 3, but it's not actually paper 3. You also know it is not paper 3. What is very important is the title, that it is Quantum Physics and Astrophysics. So this is the paper you did in the end of term, and it was strictly 1 hour. So for those of you who failed this badly, I would like to take this opportunity to help you go through this paper. And maybe as we go through, you could develop ideas and also gain confidence in dealing with this paper. Okay, so to begin with, number 1 was saying state what is meant by a photon. And throughout our class time, we have been defining a photon. So we said a photon is actually a packet of energy, of electromagnetic radiation, or a quantum of energy of electromagnetic radiation, that is a photon. Of course, we know that the energy of a photon depends on the Planck's constant h times frequency, so you lose nothing by adding that. So a photon is a packet of energy of electromagnetic radiation. Of course, me, I'm writing EM to mean electromagnetic radiation. So don't define a photon as a packet of energy and you stop there. It is a packet of energy of electromagnetic radiation, and the energy is given by Planck's constant h times the frequency. Then part B, describe the appearance of a visible line emission spectrum as seen using a diffraction grating. Of course, when a visible line emission spectrum is seen using a diffraction grating, then we mostly see colored lines, mostly colored lines. They are mostly colored lines on a darker background. So mostly they are colored lines on a darker background. If it was a line absorption spectrum, then there would be mostly darker lines on a bright background. So that is for an absorption spectrum. Okay, let's continue. An electron is initially at the energy level -0.85. State the total number of different wavelengths that may be emitted as the electron de-excites, losing energy. So let's see how many wavelengths can be emitted as the electron de-excites. Of course, since we are starting from 0.85, it may de-excite from 0.585 to the ground state. It may also de-excite from 0.85 to the first excited state, or from 0.85 to that second excited state. Those are 3. But then one which was de-excited from, say, which was, of course, even the second excited state or the first excited state, the electron is not actually stable. Therefore, it may again go further and de-excite. So it could de-excite from the second excited state to the ground state, of course, after emitting a wavelength when it was from the 0.85 to negative 1.50. Or it can also be de-excited from this level up to that level. Those are already 5. Then it could also be de-excited from this level to the ground state. So you notice that the total number of wavelengths that we could expect are actually 6. Okay, so that is the answer there was supposed to be 6. Next, photons resulting from electron de-excitation from that energy level are incident on the surface of platinum. Platinum has a work function of 5.6 electron volts. Remember, work function is the minimum energy required to release an electron from a metal surface. So determine the maximum kinetic energy in electron volts of photoelectrons emitted from the surface of platinum. We want the maximum photon energy. So the maximum kinetic energy rather. So first of all, let's find the maximum photon energy. So the maximum photon energy is going to be equal to, remember we are moving from negative 0.85, we are moving from negative 0.85 up to the ground state. So this means we shall have negative 0.85 minus negative 13.6 as the change in energy, and when you press your calculator, this gives you 12.75 electron volts. That is the maximum photon energy, but it's not the maximum kinetic energy. So remember, from Planck's, Einstein's equation, the energy of the photon is equal to the work function plus the maximum kinetic energy. So the work function has been given as 5.6, and the maximum photon energy we have obtained as 12.75. So this will be plus Emax. So we want to find the maximum kinetic energy, so we simply subtract. So we shall have 12.75 minus 5.6. And when you subtract, I think you get 7.2 electron volts. So that is the maximum kinetic energy of the photoelectron emitted. Next, the wavelength of the photon producing the photoelectron in part 1. So we want the wavelength. Remember, energy of a photon is equal to HF, which is equal to HC divided by lambda. So it means the wavelength lambda is going to be equal to 6.63 times 10 power negative 34, that is Planck's constant, then times 3 times 10 power 8, that's the speed of light, divide by of course the difference in energy between 0.85 and 13.6, which is negative 0.85 minus negative 13.6. Remember, this is in electron volts, so I will say times 1.6 times 10 power negative 19 to change it to joules. And when you press your calculator, you are most likely going to get 9.8 times 10 power negative 19. Not negative 19, it is times 10 power. Let me try to bring an eraser. So it is times 10 power negative, actually 8, not 19. Okay, so that is the question. Number 2, state an effect, one in each case, that provides evidence for the wave nature of a particle. The most important effect that provides evidence for the wave nature of a particle is, we call it electron diffraction. Electron diffraction, or you can talk about the electron microscope, because this one uses electron diffraction straight away. The electron microscope. So that is the most common. We do not talk about that is what interference. Of course, we said there are two major factors or two major properties which show that something is behaving as a wave, but we had enough proof for electron diffraction rather than for interference. So to show that a particle is behaving as a wave, then we can concentrate on electron diffraction. Then for the particulate nature of electromagnetic radiation, we talked about Compton scattering. Compton scattering or Compton effect. And here you can also talk about the photoelectric effect. You can talk about the photoelectric effect. Those are the factors, those are the effects which provide evidence for the particulate nature of electromagnetic radiation. Next, they gave us these energy levels and said for the emission spectrum associated with these energy levels, on the figure 12.1, mark with an arrow the transition that gives rise to the shortest wavelength. So to have a simple background, shortest wavelength, energy is equal to HF, which is Hc over lambda. If this is to be the shortest, then this should be the largest. That means we must have the largest energy change or energy difference. Therefore, we shall need this energy change from negative 3.4 to negative 0.50. Since this is an emission spectrum, then I can easily draw an arrow pointing downwards because an electron must have made a transition from a higher energy level to a lower energy level in order to emit a photon. Okay, next, show that the wavelength of the transition in Roman 1 is that. So we are going to show that wavelength very fast. The energy of a photon is equal to Hc over lambda, which implies that wavelength lambda should be equal to, this will be Hc divided by E, or difference in energy. I've just put here difference in energy. I'm now substituting. This will be 6.63 times 10 power negative 34 multiplied by 3.0 times 10 power negative, not negative, 10 power 8. So this will be times 10 power 8, the speed of light, divided by the difference in energy. So we are moving from negative 0.54, we are moving up to negative 3.4. Because it is in electron volts, I will multiply this by 1.6 times 10 power negative 19 to change it to joules. And when you press your calculator, you are most likely going to be getting 4.35 times 10 power negative 7 in meters. So the most important thing was around here, just subtracting the energy differences to be able to find that, that wavelength. So lambda is equal to that. Next, state what is meant by de Broglie wavelength. Of course, we have sung this several times. This is the wavelength associated with a moving particle. The wavelength of a moving particle, or wavelength associated. What is the spelling? Okay, associated with a moving particle. So it's the wavelength associated with a moving particle. Remember the de Broglie wavelength is equal to h over p, where p is momentum. So calculate the speed of an electron having a de Broglie wavelength equal to the wavelength in B, Roman 2. So we have already seen de Broglie wavelength is equal to h over the momentum. But if a particle has mass, then this will be h over m times v, because momentum is m times v. So we substitute, this will be 6.63 times 10 power negative 34 divide by 9.11 times 10 power negative 31, that is the mass of an electron, then times 4.35 times 10 power negative 7, that is the wavelength that we have obtained above. And when I press my calculator, I get approximately 1.67 times 10 power 3 meters per second. So that would be the speed of an electron having that de Broglie wavelength. Okay, next, explain what is meant by photoelectric effect. We have studied the photoelectric effect, the emission of electrons or release of an electron from a metal surface. From a metal surface when electromagnetic radiation, I'll use EM for electromagnetic radiation, when electromagnetic radiation of high enough frequency falls on it. So we need for photoelectric effect, for photoelectric emission, the radiation incident on a metal surface should have high enough frequency. That's what we call the threshold frequency. In other words, should be having a higher work function. Otherwise, photoelectric emission would not actually occur. One wavelength of electromagnetic radiation emitted from a mercury vapor lamp is that. Calculate the photon energy corresponding to this wavelength. I think that is easy. The energy of electromagnetic radiation is Hc divided by wavelength. So we simply substitute. So when we substitute, we shall have 6.63 times 10 power negative 34 for the Planck's constant, times 3 times 10 power 8 for the speed of light, divided by, this is 436, so that is 436 times 10 power negative 9 to change it from nanometers to meters. And when you press your calculator, you most likely get 4.56 times 10 power negative 19 in joules. So that will be the energy. Next, light from the lamp in B is incident separately on the surface of cesium and tungsten metal. Data for the work function energies of cesium and tungsten are given. So we can see the data here in the table. Calculate the threshold wavelength for photoelectric emission from cesium. So we know that work function is equal to H F naught, where F naught is the threshold frequency. This will be equal to Hc over lambda naught, where lambda naught is the threshold wavelength. So if I make lambda naught the subject, so the threshold wavelength is going to be equal to Hc divided by the work function. So we can substitute. So by substituting, this will be 6.63 times 10 power negative 34, that is Planck's constant, then times 3 times 10 power 8, that is the speed of light, divided by the work function for cesium, which is 1.4 but is in electron volts. So I have to multiply this by 1.6 times 10 power negative 19 to change it to joules from electron volts. When I press my calculator, this gives me around 888, or I can just conclude as 890 nanometers. 888 nanometers. Of course, I have divided by 10 power negative 9 to change it from meters to nanometers. Here it is in meters, but when you divide by 10 power negative 9, it will be in nanometers. Then for tungsten, still I'll just use this expression. The threshold wavelength is going to be 6.63 times 10 power negative 34, then times 3 times 10 power 8, divide by the work function is 4.5 times 1.6 times 10 power negative 19. Of course, I'm going also to divide by 10 power negative 9 so that people will know or see that my answer will directly become nano rather than just meters. So this will give me 200 and press the calculator, that is 280 nanometers. So the wavelength, lambda naught, the threshold wavelength is 280 nanometers. Okay, then use your answers in C to state and explain whether the radiations for the mercury lamp of wavelength 438 nanometers will give rays to photoelectric emission from each of the metals. So number one, for cesium. Cesium, you look at the threshold wavelength. Look at the threshold wavelength. Before we look at that, let's briefly go back to this part here. You see the wavelength was giving us energy of this. If you want, you can try to change it to electron volts and see. But then, if you're very observant, just using the wavelengths, since they said use your answers in C, you can see that this one will cause photoelectric emission, so I'll say that this one will cause. Yes. Reason? The wavelength which is of the lamp, which is 436 nanometers, is actually less than the threshold, which is 890 nanometers for cesium. Remember, threshold wavelength is the maximum wavelength above which no photoelectric emission occurs. So since 436 is less than 890 nanometers, then photoelectric emission can occur. For tungsten, we shall say no. Reason? The wavelength of the rod of the lamp, of the mercury lamp, which is 436 nanometers, is actually greater than the threshold, because here the threshold is 280 nanometers. Remember, if the wavelength is greater than the wavelength of the radiation is greater than the threshold, it means the frequency is less than the threshold. Therefore, photoelectric emission cannot occur. Okay, so that was that question. Next, we can proceed. By reference to photoelectric effect, state what is meant by threshold frequency. We said threshold frequency is the minimum frequency. The minimum frequency of electromagnetic radiation. The minimum frequency of electromagnetic radiation needed to emit electrons from a metal surface. It is actually the minimum frequency of electromagnetic radiation needed to emit electrons from a metal surface. The frequency of electromagnetic radiation below which no photoelectric emission occurs is also the threshold frequency. That frequency of the electromagnetic radiation below which no photoelectric emission occurs is called the threshold frequency. Part B. Electrons are emitted from a metal surface when light of a particular wavelength is incident on the surface. Explain why the emitted electrons have a range of values of kinetic energy below a maximum value. So we know that the maximum kinetic energy corresponds to an electron emitted from the surface. In other words, it is electrons from the surface which have the maximum kinetic energy. So electrons electrons emitted from the surface will have maximum kinetic energy because they require less energy to set them free. But an electron below the surface requires energy to bring it to the surface. An electron below the surface requires energy to bring it to the surface. And if this is true, it means the surplus energy to be given to this electron as kinetic energy will be less. So that means it makes sense to say that it will be less than Emax. So electrons emitted from the surface have maximum kinetic energy. They have Emax. Then an electron below the surface will require energy to bring it to the surface. So this will be less than the maximum kinetic energy, Emax. Next, the wavelength of the incident radiation is with lambda. The variation with 1 over lambda of the maximum kinetic energy, Emax, of electrons emitted from a metal surface is shown in the figure. So we can see our figure here. Use the figure to determine without reference to work function energy, the threshold frequency F0, without reference to the work function energy. We want to find the threshold frequency. So, number one, the graph. We are going to use the graph. So when you extend this graph, of course, it will stop. You can use a ruler. If you have this printed, you can use a ruler to extend this line. I think it stops around here. You can use a ruler. You prolong this line. It will be around here. And this value here is actually 1.8, actually 1.85 times 10 power 6, that is per meter. So it means from the graph we are seeing that 1 over lambda naught is equal to 1.85 times 10 power 6. But we know that from the general wave equation, we know that frequency is equal to c over lambda. So c will be the 3 times 10 power 8. So this is going to be times 1 over lambda naught, which will be times 1.85 times 10 power 6. Of course, you can't divide because this is 1 over lambda naught. It is not lambda naught, but it's 1 over lambda naught. That's why you say I have multiplied here. And when you press your calculator, you get this as 5.55 times 10 power 14 hertz as the threshold frequency. Next, use your answer in Roman 1 to calculate the work function. Use your answer in Roman 1 to calculate the work function. So use your answer in Roman 1 to calculate the work function. So work function phi is equal to h times f0. That is very simple. So we simply substitute h times f0. This will be 6.63 times 10 power negative 34 multiplied by f0, 5.55 times 10 power 14. When I press my calculator, it is giving me 3.68 times 10 power negative 19 joules. You can check your calculator. Cesium metal has a work function of that. You notice that this work function is smaller than that. And if this work function is smaller, remember work function is equal to Hc over lambda naught. In other words, it is hc times 1 over lambda naught. So you notice that the work function is now smaller. And if the work function is small, it means 1 over lambda naught should also be smaller. The quantity 1 over lambda naught should also be smaller. In fact, you can even try to calculate it. We can try to calculate it. 1 over lambda naught is going to be equal to, this will be 2.2 times 10 power negative 19. That is the work function, divided by hc, which is 6.63 times 10 power negative 34, then times 3 times 10 power 8. And when you press your calculator, you get approximately 1.1 times 10 power 6. So the work function, 1 over lambda naught, the new value of 1 over lambda naught is approximately 1.1 times 10 power 6. So this takes me back to the graph. So on the graph, we have to draw a line. Of course, the line will be parallel to the one which is already there. Extremely parallel because they have the same gradient. So the line should be extremely parallel. But this time, the line is going up to 1.1. I think from the scale, 1.1 is approximately here. So using your ruler, you are going to draw a straight line which has the same gradient as this. Let me try to estimate this. So because I'm not using a ruler, my line may not be very accurate, but for you are going to use a ruler. And your line should be very accurate. Extremely parallel. Your line should be extremely parallel to the one which is already there. So you could see that that is our new line. You could see that that is our new line. Okay, next. By reference to photoelectric effect, explain what is meant by work function. Work function. What is meant by work function? So work function energy is actually the minimum energy of photon, the minimum photon energy or the minimum energy of electromagnetic radiation, the minimum energy of electromagnetic radiation required to remove, which is required to remove an electron from a metal surface. The minimum energy of electromagnetic radiation required to remove an electron from a metal surface, that is the work function energy. Next, show that a photon of this light has an energy of 3.5 times 10 power negative 19 joules. So they have given us the area as this, the power as that, the wavelength as that. So energy of a photon, we already now know that energy of a photon is equal to hc over wavelength, which will be 6.63 times 10 power negative 34 for Planck's constant, then times 3 times 10 power 8 for the speed of light, divided by the wavelength, which is 570 nanometers, that is times 10 power negative 9 meters. And when you press your calculator, you most likely get 3.49 times 10 power negative 19 in joules, which to two significant figures rounds off 3.5 times 10 power negative 19 joules as required. Then calculate for a time of 1 second the number of photons incident on the surface. For a time of 1 second, calculate the number of photons incident on the surface. We know that power is equal to energy over time. So it will be total energy, which will be the number of photons times the energy of each photon per unit time. So we want the number of photons incident on the surface in a time of 1 second. So this will be equal to energy divided by power. So this will be actually not energy divided by power, it is power divided by energy. This will be the power divided by energy. So we substitute. When we substitute, we shall have 2.7 times 10 power negative 3 divided by 3.5 times 10 power negative 19. When you press your calculator, okay, this is 7.7 times 10 power 15. That is the number. Then the change in momentum of the photons. So since we have the number of photons, we can find the momentum of just one photon using the de Broglie wavelength, the formula for de Broglie wavelength. So momentum is equal to h over wavelength. So this would be 6.63 times 10 power negative 34 divided by 570 times 10 power negative 9. This gives us 1.16 times 10 power negative 27 as the momentum of one particle, of one photon. Then the total change in momentum is going to be equal to 1.16 times 10 power negative 27 multiplied by 7.7 times 10 power 15. And when I press my calculator, okay, this gives me 8.96 times 10 power negative 12. Many of you, you failed this question because you thought this was the answer here, but this was the momentum of just one photon. And yet we have 7.7 times 10 power 5. Power 15 photons. So you had to multiply by the number of photons. Okay, next is the pressure. By definition, pressure is the force acting normally per unit area. So pressure is going to be equal to force over area. But remember, force is the rate of change of momentum. So this will be change in momentum per unit time divided by area. Remember, the time was 1 second. So it will mean that I'll just get 8.96 times 10 power negative 12 divided by the area, which is 1.3 times 10 power negative 5. And this gives me 6.9 times 10 power negative 7 pascals. Okay, next. White light is incident on a cloud of cool hydrogen gas, as illustrated in the figure. The spectrum of the light emerging from the gas cloud is found to contain a number of dark lines. Explain why dark lines occur. Explain why dark lines occur. I think we have explained this several times. So why do we have dark lines? So we know that the electron absorbs only photons whose photon energy is equal to the difference in energy levels, or the difference in the energy of two energy levels. So we know that photon energy or photons, a photon of energy equal to difference in energy, photon of energy equal to difference in energy of two energy levels is absorbed by an electron. So the electron does not absorb any photon. It only absorbs a photon whose energy is equal to the difference in the energy of two energy levels. So the electron has now absorbed a photon. But on electron de-excitation, so of course when it has absorbed a photon, the atom is excited. So on electron de-excitation, photon of the same energy is going to be re-emitted. But this time it is re-emitted randomly in any direction or in all directions. Which means that only a part of the re-emitted light could be in the original direction. So as light goes through the hydrogen gas, the atoms have their electrons absorbing some of these photons, whose energy is equal to the difference in the energy of two energy levels of the electron. So the electron is said to be excited, or the atoms are said to be excited. Then on electron de-excitation, the electron must emit the same energy, but this time the electron emits that energy randomly in all directions or in any direction. And if this occurs, it means only a part of the re-emitted light could be in the original direction of the beam. So it means there is a possibility of some part of the light not to be re-emitted in the same original direction, and therefore that part of the light will be missing on the screen, resulting into dark lines. Okay, I think we have explained that several times. Next, some electron energy levels in a hydrogen atom are illustrated. So they have illustrated them here. One dark line is observed at a wavelength of 435 nanometers. Calculate the energy in electron volts of a photon of light of that wavelength. These are easy questions. When you do them many times, you become an expert. They now start boring. So energy is equal to Hc over lambda. So this will be 6.63 times 10 power negative 34. This is times 3 times 10 power 8 divided by the wavelength, which is 435 times 10 power 9. And when you press your calculator, I think this gives you a 4.57 times 10 power negative 19 joules. This is in joules. The answer is required in electron volts. So I'll go ahead and convert to electron volts. 4.57 times 10 power negative 19 divided by 1.6 times 10 power negative 19. This is to electron volts. When you press your calculator, so to three significant figures, I have 2.86 electron volts. Okay, next. On the figure, draw an arrow to indicate the energy change that gives rise to the dark line. The energy change that gives rise to the dark line. So 2.86 electron volts. Let's try to check. Get your calculator. You subtract the energy differences. Let's check. Negative 0.55 minus negative 3.41. I think this gives you, let me check. I think this gives you 2.86. Remember, an electron absorbs a photon whose energy is a difference in the energy levels. So it is from negative 0.55 to negative 3.41. Therefore, I'll draw a line from here up this. Of course, you could draw one pointing upwards, but after all, this is re-emitted randomly in any direction. That's why it is actually a dark line. So that will be the transition from negative 0.55 to negative 3.4. Okay. Next, of course, this is no longer quantum physics. Of course, this is actually astrophysics. So number 7 is astrophysics. State Hubble's law. We know Hubble's law, the recessional velocity or speed of a galaxy moving away from the Earth is proportional to its distance from the Earth. So the recessional speed, recessional, the recessional speed of galaxies moving away from the Earth is proportional or is directly proportional. You can add there directly proportional to their distances from the Earth. So that is Hubble's law. Now note that Hubble's law is only applicable to distant galaxies. We can't apply it to objects in our own galaxy. So that's why we say the recessional velocity of galaxies is directly proportional to the recessional speed of galaxies is directly proportional to their distance from the Earth's surface. Numerically, this or algebraically, this will be v equals to h naught times d. The speed is directly proportional to distance, where h naught you call it the Planck's constant, not Planck's constant. H naught you call it Hubble's constant. Okay, next, explain why the energy levels are negative. We explained why energy levels are always negative. We said an electron at infinity is completely free from the force of attraction, therefore it should be having the greatest amount of energy. But remember, electrons are tightly bound to the nucleus. That means if you try to take it to infinity where it should be completely free with the greatest amount of energy, then you should add energy to it. It should be gaining energy to leave the atom. It should be gaining energy to leave the atom. And yet the total energy of an electron in the atom is less than that of a free electron. So what does that mean? It means the energy of free electrons is zero, and when the electron leaves the nucleus or moves away from the nucleus, it gains energy. That means if it gains energy tending towards zero, elsewhere it must be negative. Therefore, we are saying electrons are tightly bound to the nucleus. Electrons are tightly bound to the nucleus and must gain energy they must gain energy to leave the atom. The total energy the total energy of an electron in the atom is less than that of a free electron. Is less than that of a free electron. Remember, for a free electron, the energy is 0. So for a free electron, the energy is 0, and yet electrons are tightly bound to the nucleus. Therefore, they must gain energy to leave the atom. So when they leave the atom, they are gaining energy. But for a free electron, the energy is 0. That means elsewhere it should be less than 0. That's why it is actually negative. Okay? An electron makes a transition from level C to level A. Can show the energy gained by the electron in electron volts. Level C to level A. So that means it is negative 3.4 minus negative, no, level C to level A. Okay, let me start with the highest. Level C to level A. I will start with the highest. Negative 0.85 minus negative 3.4, and this gives me 2.55. So that energy is 2.55 electron volts. Then calculate the wavelength of the photon absorbed by the electron. So wavelength, from the equation, wavelength is going to be hc over E. I just made lambda the subject. 6.63 times 10 power negative 34 times 3 times 10 power 8 divided by the energy is 2.55, change it to joules, times 1.6 times 10 power negative 19. Because the answer is needed in nanometers, I'll go ahead and divide by 10 power negative 9 to change it to nanometers. And when you press your calculator, this gives you times 10 power negative 9. This is dividing by times 10 power negative 9. So this gives you okay. So this is approximately 490 nanometers to two significant figures. Next, light from a distant galaxy is passed through a diffraction grating. The figure below shows the part of the spectrum of light that shows a strong hydrogen alpha emission line. State how an emission line is produced. An emission line is produced when electrons make a transition from higher energy levels to lower energy levels, losing energy as they emit photons. So electrons make transitions. Or an electron, let me consider just one. How an emission line. So electron makes transition. An electron makes a transition to lower energy levels. Losing energy as it makes that transition. It is losing energy as it emits a photon. So as the electron makes a transition from a higher energy level to a lower energy level, when it is losing that energy, it emits a photon. That photon it re-emits corresponds to the line, the line spectrum. Then state an adjustment that could be made to the experimental arrangement that would space the emission lines more widely. Remember, this is going through a diffraction grating. Okay, and we know for a diffraction grating, we know that d sine theta is equal to n lambda. So it implies that sine theta Actually, sine theta is inversely proportional to d, which also implies that theta is inversely proportional to d. So we want an adjustment that could be made to the experimental arrangement that would space the emission lines more wide. That is, theta increasing, d should be decreasing. So therefore, we have to reduce the grating, slit separation. We should reduce the grating slit separation, or alternatively, we could increase the distance between the grating and the screen. Of course, when the screen moves away from the grating, the lines move further apart, or theta actually it's like they move further apart, the angle increases. So alternatively, we could increase the distance between the grating and the screen. Okay, so next in the laboratory, the wavelength of the hydrogen emission line is 656.3 nanometers. Use the figure above to determine the recessional velocity of the galaxy. So of course, this is the redshift. We know that the redshift equation, delta lambda over lambda is equal to V over C. So we want to find V. So V is going to be delta lambda over lambda times C. Okay, so V is going to be the difference in wavelength. The difference in wavelength will be in the laboratory, we have this wavelength, but light from a distant galaxy is showing that this is approximately, I think it is at the center, 661, around 661.5, somewhere here. You can use a ruler on your paper. So this will be 661.5 minus 656.3. That is the difference in wavelength. Divide by the wavelength, of course, in the laboratory, 656.3. Multiply by the speed of light, which is 3 times 10 power 8. And when you press your calculator, you press mine. Okay, my calculator gives me 2.4 times 10 power 6 meters per second. I don't know what you got, but you can check. Next, suggest why hydrogen spectral lines play an important role in determining redshift. We know that most of the stars have hydrogen in abundance. So because of the relatively high abundance of hydrogen in stars, then we can rely on the hydrogen spectral lines to determine the redshift of galaxies. So here we are saying a relatively high abundance. There is a relatively high abundance of hydrogen in stars. That's why we rely on hydrogen spectral lines. Next, they gave us a graph of the recessional speed v against distance d for some galaxies. Deduce the Hubble's constant. H naught from the graph and explain your answer. So we want to deduce Hubble's constant. Remember, Hubble's law states that the recessional velocity is directly proportional to the distance. That means if it is a graph of v against d, so Hubble's constant h naught must be equal to the gradient. If Hubble's constant equals to the gradient, I will take as simple values here. Maybe I can take this value here, where on the y-axis, have it here. That is 1, 2, 3, 4, 5. The scale on the vertical, I think it is 0.2. Is it 0.2? No. So that is 2 divided by 5, 0.4. 1, 2, 3 times 3. So this is 5.2 minus 0 divided by, on the x-axis we have 2.0 minus 0. The numerator you have times 10 power 6. In the denominator you have times 10 power 24. So you can press your calculator. 5.2 divided by 2. So this is giving me 2.6 times 10 power negative 18 per second. So it means the Hubble's constant is going to be 2.6 times 10 power negative 18 per second. Every calculation of Hubble's constant will give us the power times 10 power negative 18. Last question. Name the term used to describe an astronomical object that has a known luminosity, that is a stellar candle. We saw this. Not stellar candle, standard candle. Standard candles are those astronomical objects whose luminosity is known. That is a stellar candle. I mean a standard candle. I don't know why I like calling it stellar candle. Standard candle. Then next, determine the distance of the star from the Earth. So they gave us its luminosity. They've given us the radiant flux intensity. We know that the radiant flux intensity F is equal to the luminosity divided by 4 pi d squared. So this means that the distance we want, d, is going to be equal to the square root of the luminosity divided by 4 pi f. 4 pi f. And if we try to substitute, the distance is going to be equal to the square root divided by the luminosity, which is 4.8 times 10 power 24 divided by 4 pi times, this is 2.6 times 10 power negative 9, because it's given nanowatts per meter squared. And when you press your calculator, I'm pressing mine, you can also press yours. Okay, my calculator gives me 3.8 times 10 power 18 in meters as the distance of the star from the Earth. Next, the sun has a surface temperature that the wavelength of the light for which the maximum rate of emission occurs is that. The scientist observing the star in A finds that the wavelength for which the maximum rate of emission occurs is that. Show that the surface temperature of the star in A is approximately 6,700. So we know that from Wien's displacement law, lambda max times the temperature T, absolute temperature, must be equal to a constant. A constant. Why do I write constant instead of constant? Must be equal to a constant. So it means we shall just use this expression here. So let's think of the sun. The wavelength is, I will not convert the units, 500 nanometers. The surface temperature, 5800, should be equal to, for the other star, its wavelength is 430 times its temperature T. So making it the subject, so T is going to be 500 nanometers divided by 430 nanometers times 5800. When I press my calculator, 500 divided by 430 times 5800. So this is giving me T as 6,744, which is approximately 6,700 Kelvin as required. And lastly, use the information in A and B Roman 1 to determine the radius of the star. So to determine the radius of the star, we shall use Stefan Boltzmann's law. Luminosity is equal to 4 pi r squared sigma T power 4. This is Stefan Boltzmann's constant. So the radius is going to be also the square root of the luminosity divided by 4 pi sigma T power 4. We now substitute. This will be the square root of the luminosity is 4.8 times 10 power 29 divided by 4 pi times 5.67 times 10 power negative 8, then times 6,700 power 4. This 5.67 times 10 power negative 8 is Stefan Boltzmann's constant. So when you press your calculator, let's press the calculator. Okay, from my calculator I get 1.83 times 10 power 10. 1.83 times 10 power 10 meters. So that is actually the radius of that star. I think that was the end of this test, of this exam, and I think I've tried my level best to go through it. Thank you for watching this video, and do not forget to subscribe, share with your friends studying physics A-level Cambridge, and have a good day. Enjoy your holiday. Bye bye. See you.